Okay, so I'm going to talk about the primitive types. Primitive types of any programming languages are the types of storage that you can declare that the language defines for you. You don't have to define it yourself. So, for example, in Java, Java basically copied the same set from C and C++, except that they added the byte and the boolean. So boolean is a type of a piece of storage that has the value of either true or false. The way it's represented in storage, it's actually represented with one bit. So if the bit is on, that would mean it's set to true, and if the bit is off, that means it's set to false. If you don't initialize it, it will be set to false by default. So basically I have the primitive types here, what their contents are, what their values will be if you don't set them, and then how much space they take up. So a bit will take up, a boolean will take up one bit, and then if we have maximum and minimum values, so it's really applicable for boolean. A character, which is the characters you see on the screen, A, B, C, 1, 2, 3, any of the characters that we could represent on the screen. In Java, they take up 16 bits, and in C and C++, they actually take up 8 bits. The new type that was added was byte, which is also 8 bits that we could use to represent signed integers. So a signed integer is an integer value. That means it's a number, but there's no fractional part. And the sign means we could have a positive value or a negative value. So you could represent numbers like -3 or 52, something like that. As long as the value you're trying to represent can be held in the size of the storage that the compiler is going to ask the operating system to allocate for you. So then you might think, why don't we use big numbers? So then, for example, we could go to short, which is the next biggest size, which is 16 bits. So the values that we can store in 16 bits range between -32,768 and positive 32,767. With only 8 bits, we can represent numbers between -128 and positive 127. So then the next biggest integer, the next biggest signed integer, is the primitive type called int, int. That allocates 32 bits of storage. If you don't supply a value, it'll default to 0. And then I just have very large numbers here as the minimum and maximum. If you want to represent a really, really large integer number, you could use a long. Longs take up 64 bits, and therefore their minimum and maximums are really, really huge. If you decide you want to represent numbers that have a fractional part, you could do that by using a type called float. That's a floating point number. That means there's a decimal component to it. 32 bits is used to represent those numbers, and they're signed numbers. They follow the IEEE 754 floating point format, which means one of the bits is dedicated to there being the sign, positive or negative. A certain number of bits is dedicated to, well, the representation ends up being, there's a component for, well, I won't get into how they're represented. It's not pretty straightforward, but basically it's a magnitude and an exponent. But anyway, eventually those numbers get converted back to something that would appear on a screen that we would understand. But actually, if you want to know how those numbers are represented, as in the computer architecture course, there's a lecture where that's discussed. Okay, so we can now declare if we want to write out characters or declare storage for numbers, and then we could start filling in those fields as we start the program. So some of the operations that can be performed on these primitive types are operations that show up here. For booleans, you can make statements that, as long as the statement resolves to either true or false, we could take that result and then assign it to a boolean. So if we had a boolean, b, we could say, and let's say I, and we said before I would be initialized to 0 if you don't assign it. So right here, right now we're declaring a 1-bit piece of storage for a boolean, and we're declaring 32 bits of storage for the integer I. And it's currently set to 0. So this statement is basically saying, inside this parentheses is a true or false statement. We're saying I is not equal to 0, which in this case would be false, because I is equal to 0. So as a result of this line, this boolean will be set to false. Okay? And then we could take characters and sign them. Actually, I think this should be a single quote. We'll double check that in a second when we compile. But we can declare a piece of storage called C, which is of type character, therefore it takes up 16 bits, and we can assign it to the character capital A. We can perform operations on certain members of these primitive types. For example, numerical values can have multiplication and addition, division, subtraction, powers, anything that makes sense mathematically we can do. You couldn't multiply two characters together because that doesn't make sense, right? 8 times b does not make sense. But 3 times 4 times 5 would make sense. We could do mathematical statements. For example, if m and n are already defined as integers, we could say n is equal to 5. Then by putting parentheses around this says, what is the value of this? The value of this is 5, and then 5 gets copied to the storage location m, assuming m is also a numerical primitive type, not a character. We could make a statement in Java that says 3 times 4. That will compile. It makes sense. You can say 3 times 4. But we're not assigning this to anything, and nothing's actually happening with it. So it will compile, but it doesn't make much sense. We could put this, a very common task to do in computer programming is to take a certain number and add 1 to it. That's very common. So you might expect to say n equals n plus 1 would be commonly done in computer science. They tried to make it a little bit of a shorthand thing by just saying anytime you see a plus and a plus, that means add 1, since that's a very common thing. So it saves 1 or 2 keystrokes. Instead of saying n equals n plus 1, n equals n plus 1, that's 5 characters. We now have 3 characters. So we save 2 characters. And here's another way to say, take a number and then say plus equals 1. You could say plus equals 3, and then it'll add 3 to the current number. 2 minus signs in a row will decrement the number. Minus equals will decrement the number.
I'm sorry, with the
Sure.
with the n plus equals 1.
Right?
Okay, if you put 3, then obviously every time you put n plus, it's going to add 3.
Right. If you say
Okay.
n plus equals 3, that's a shorthand way of saying n equals n plus 3.
Okay.
So basically we'll say we don't have to repeat the n, n equals n part. A lot of times you'll do operations on the number itself. So you take its current value and then alter, make it go up or down. So they try to come up with a lot of shorthand. And some people will say it's good programming practice never to use this. Really spell it out. Take the extra fraction of a second and write n equals n plus 1. That way nobody will ever be confused what you mean. Someone might look at this and they haven't seen this in 20 years and go, what does that mean again? So anyway, these are some shorthand things that they've decided to do. And then one that's a little bit dangerous, I'll just go down to this one, is the double equal sign. So you can imagine you could have a variable called a and you want to say a equals b. So that means take the value of b and copy it over to a. There might be other times where you want to say if a is equal to b, then I want to do something. You're not looking to transfer numbers around. You're just asking the question, the true or false question, does a equal b? So you might think they would use the same equal sign. So to kind of remove that ambiguity, if you're asking the question, does a equal b, use two equal signs. So this is really the question, does a equal b? And that will either evaluate to a true or false statement. What's dangerous is you could say if, open parentheses, close parentheses, and I can even do this when we turn the computer on. You could say if a with one equal sign b equals b, what will actually happen is the contents of b will get copied over to a, and then after that's done we'll check to see if they equal, and obviously they're going to equal each other at that time, and that might not be the result you want. So that is one kind of danger that's going on. And then we could take these boolean expressions, any expression that evaluates to true or false, we could start building on them by saying if one scenario is true, and in addition to that we need another scenario to be true. So maybe we could have a statement that says if a equals b and b does not equal 20, maybe that's our condition that makes us decide if we want to proceed, we can do that. So we can say if a, in parentheses, if a equals b, and then we do two and signs. And then we could put our second condition. We could also or conditions together. If a equals b or b is greater than 0, that could be our true or false statement. We could also decide to say not equals. Some programming languages have the less than greater than to mean not equals, but Java uses exclamation point with an equal sign following it. And then this combination of a question mark and a full colon, we could say, is this statement x less than y? If so, if true, we do whatever x is, and if false, we do whatever y is. So it's a little shorthand for an if then else statement. Okay, so if we were to then go and write code, this is a piece of code that so this is a piece of code that uses these primitive types. And all I'm really doing here is just declaring this storage and filling it in with values. So this is a piece of Java code. So a little reminder, the outer class has to have the same name as the file. That's just one of the rules of Java compiling. And then there has to be at least one method called main, which is, once we compile it, that's going to be the entry point where we start from. And then we could have a series of classes after that. And the main method has to be static. Static, as we'll talk about later in the class, means one version per class, not one version per object in the class.
Never got that yet.
Okay.
As confused about that as can be.
Okay, well that actually, one of the things difficult about Java is when you're first learning it, it forces you to kind of know everything about object-oriented programming just to write your first program, but hopefully it'll make a little bit sense later on. So anyway, what I'm doing here is obviously I'm just exercising the primitive types. I'm just saying I'm declaring an integer called I, setting it equal to 2. I'm declaring a character called C, setting it equal to A. A byte, if we remember, bytes only take up 8 bits of storage. Oh yeah, one of the things I was talking about before is, why wouldn't we just declare really big numbers, big stores? That way we never have to worry about the number getting too big or too small. Well, the answer is you might want to not use, you don't want your program, you might not want your program to use up a lot of storage. If we have millions of numbers, and we know they'll never go higher than 10, we don't need to take 64 bits to times a million. We don't need to take up that much space. So it's really a judgment call which types of integers and floats you want to use, the big ones or the little ones, depending on your anticipation of how big or small your numbers will get, and if you care about using up that much space or not. So, in this case, filling in, yeah, the character with the letter A, a byte with the number 127, which we think it'll accept it. A floating point number, now actually when you assign it, a floating point number we said can hold decimal values. So I'm saying this is equal to 3.5, but I have to put an F after it, meaning I as the coder realized I only have a certain amount of space, and I believe this number will take up no more space than is needed. So I'm identifying this floating point number as a floating point number. Doubles, which are floating point numbers but take up a lot more space, I don't have to say that. And then booleans can take on the value of true or false. And all I'm really doing here is just spitting out the values that come in. So there should be no great surprise that the numbers should come out exactly the way they are, but I'll compile it anyway. So compiling is Java C, Java. Okay, and then to run it we say Java print. Okay, so that was kind of expected. Now, let's just look at some of the things for example, let's make our notes say, make sure that's accurate. Our notes say for bytes, we can, I'm sorry, if we declare something as a byte, it's a signed number, so of the 8 bits of storage we're given to represent this number, the first bit tells us if it's positive or negative, the next 7 bits give us the value, and 7 bits in binary can only go up to 127. So, we should not be able to represent a number like 128 with a byte, right?
Okay.
Anything above 127 can't fit, so we would expect some kind of a compiler error here. So let's see what happens. Oh, I didn't save it, sorry.
And there it is.
Yeah, so it's saying possible loss of precision. It didn't generate the class for us. Yeah, it didn't generate class for us. It would have wrapped around and become a number like negative 128. So, and let's see if we can put in 128. That should be allowed. Okay. Let's see how it comes. Okay, yeah, it comes out as negative 128. So that's allowed, but we can't do negative 129 according to our notes, because that's too big. Yeah, loss of precision again. Okay. So we just want to push these values over the limit. Now let's look at, set this back to a number it can handle. Should be able to handle negative 5. And what if we were to set a Boolean? We notice Booleans take on the value, they're a bit, so they only take on the value 0 or 1. The compiler is converting them back to true and false so that we can see it, so it makes sense to us. But you'd think we'd be able to set a Boolean to 1. I actually don't know the answer to this. It might be a
Yeah, we didn't go over that.
You think it'll say not allowed?
Yeah, probably, because it has like its default value.
Right.
It's I don't know.
Well, maybe not because it's default value, but I'm trying to put a value in that it doesn't understand. I'm hoping it'll take it, but it looks like we got an incompatible types error. So it's basically saying 1 and Boolean don't. An integer and a Boolean. It found an integer and it was requiring a Boolean, so it won't take that. It won't take 0 either. In C and C++, it will take this with no problem. And a lot of people argue that's not good. Yeah, this is not good. Okay. So we have to say something like false or true. It's the only thing we'll accept. Now, would you want this to happen? So we now initialize the storage up here. We can now start adding lines of code that move the storage around. And let's say we wanted to say the integer equals a float. Should this make sense? Or should this be allowed? Now I guess this is, so here's what we're doing. I'm declaring storage here. The I, the C, the B, the F, the F, the D, and I made this an X because byte and Boolean both begin with a B. We could actually pick any letters we want for the storage, right? We could
allowed?
Yeah, so now what are we doing here? We're taking an integer, which is 32 bits of storage, and it cannot take on values that have decimal points. Floats are also take up 32 bits, but do allow some room for the decimal point. So that's why we were allowed to put a 3.5 in the F field.
So you're trying to transfer the float to the I and T?
Right, so I'm basically trying to take the 3.5, which is stored in a primitive type floating point, a float, and transfer its value into an integer which only accepts numbers without a fractional part, just full numbers.
Yeah, so I would say no, but I don't know if the transfer would be coded or coated.
Yeah, so
that the decimal can't be right.
Okay, so...
But then why would you even do that? Because you need it to execute regarding its value, so...
Well, let's say for some reason, let's say you did some big computation using a floating point number, and then when you were finally done, you needed to just know its integer part. Or, for some reason, let's say this happened. Okay, first of all, it wouldn't make sense to put an integer into a character. That's almost making no sense, right? But we can try that in a second, just to see if it works. But suppose somebody wanted to do this. What the topic I'm basically talking about here, and this will come up later when we do non-primitive types. So basically, non-primitive types will be things that we define ourselves. The compiler wouldn't make sense to the compiler. So for example, if you wanted to define a baseball team, the compiler doesn't know what a baseball team is, but you can make a collection of 9 players with a first name and a last name and what position they play, and it might make sense to you, but it doesn't make sense to the compiler. So we'll be able to teach the compiler how to define things besides integers, characters, bytes, floats, things that make sense to us that don't make sense to the compiler. We'll be able to define it, and they'll be able to handle it. But right now we're just talking about the primitive types, and what I'm talking about now is taking one type that's somewhat similar to another type and saying, can I transfer its value over, or will the compiler say they're incompatible types? So for example, I try to put a 1 into a Boolean and the compiler said, I don't know what you're trying to do. I was kind of hoping the compiler could figure out what I was trying to do, but it doesn't. So in this case, would this be allowed? Or do you think we'll get an incompatible types error?
I would say incompatible types.
Okay, so let's... But you can kind of see why somebody might want to do this. So if we compile this, let's see. I thought this Boolean problem? No, I didn't save it. Okay. Okay, so it's saying it found a float, but it was looking for an integer, and it considers that an error. Okay. So yeah, so you got that right. But you could kind of see that somebody might want to do this. And they're close enough in type.
Because it's reminding me of, what was it with the readable file last week?
Okay.
We went over.
Where
It gives you a space of not writing directly to memory.
Oh, a buffer.
Buffer.
Thing. Yeah, a place where you can write temporarily. And,
yeah, almost like it's like someone doing that, they're trying to kind of disguise or encase
the
value.
Okay.
Is how I'm looking at it. But because the first is INT, it's defining its capabilities right there.
Okay. Yeah, so it's without a doubt, if this thing successfully happened, the fractional part would have to be gone, because this thing can't hold a fractional part. So there'd have to be some kind of either round off or round down issue. But you could kind of see why someone might want to do this. Now, suppose somebody wanted to move a floating point number into a double number. Now, what a floating point number we said was 32 bits that represents a number with a fractional part. A double is 64 bits that represents a number with a fractional part. So it's just more space to hold the number.
It's a double float.
Right, it's a double, twice as many bits to represent a float. So do you think should that one have a problem? If
I don't think so.
Let's put the double into the float. Now the types are exactly the same, there just has to be a conversion to represent it with 64 bits instead of 32. So do you think this would have a problem, an incompatible types problem? It actually does.
Because wouldn't it have to be
Oh, I'm sorry.
more like D equals F2 or 2F or something?
I'm sorry, that one does make sense because you might not have enough room. This way, can the double take the F? Can the double take the float?
Yes.
See if this has a problem. Yeah, in this case, no, I didn't save it, sorry. Keep doing it. Okay, that one it took. That one the compiler decided, even though the types are different, it really doesn't matter here. Because an F contains a floating point number, which is an integer plus a fractional part. A D contains an integer plus a fractional part, but just more bits to represent the number. Clearly, any value that could fit into F will fit into D. So this transfer, even though these two types are different, the compiler says, fine. I know there's no problem here. The reason why when it was reversed, it wouldn't allow it is possible the number we're putting in, the D, is so big it can't fit in the F. And it should give us, more than a warning because we wouldn't have control over what's in the F. So you can start to see that it starts to get a little bit hazy now. As far as these types, if we start to put one into the other, if the compiler says, yeah, I see no problem, it lets it go through. If it sees a problem, it might not let it go through. But what we can do, suppose we wanted to explicitly say, do it anyway. It would be nice to have this option, right? If we're trying to write one field into another field and the compiler's saying, I don't think you know what you're doing, I'm going to not allow this, you might say, it would be nice to say, I know what I'm doing, I'd like to do it anyway. So what we can do is what's called a type cast, where we are changing, we're taking a number on the right side and saying, I'm trying to put it into a field that's of a different type. And I know the compiler's not going to take it, but I want to say, take it anyway, right? We can do that by doing what's called a typecast. So let's go back to the one that didn't work. We were trying to put into an integer, we were trying to put a float, which doesn't make sense because the fractional part won't work. So let's just make sure we have our error again. Okay. Found a float, required an integer, so there's a problem. Okay. What I'm going to do now is just before this float, I'm going to put in parentheses int, meaning take the float, I'm telling the compiler to take the float, which is equal to 3.5, 3.5, figure out how to convert it into an integer. Once you've converted it into an integer, take that result and put it into I. So that's really what's going on here. So this is kind of, we're overriding the compiler. The compiler is trying to protect us, but we're going to override it by saying, I know what I'm doing, I want to put the float in the integer. Let me save it, and then let me compile it. And now compiled with no problems. What do you think the number, this is really a compiler design question, what do you think it'll come out to be? So the choices are, the integer was originally set to 2. I'm now taking 3.5. I'm saying convert it to an integer. And then when you're done converting it to an integer, then stuff it into I. So if it won't accept it, it'll be 2.5. I'm sorry, it'll be 2. If it converts it, it's either going to, what's it going to convert it to? Not 3.5. It's going to take 3.5 and convert it into an integer. Should it round up, round down? And this is really, there is no right or wrong. The people who came up with the compiler decided how to do this, but what would you guess it would be, if you had to guess?
I equals INT, and the F is being transferred to the INT?
It's been, so the floating point number, which is currently equal to 3.5, is going to be converted into a type for an integer. So obviously we're getting rid of the fractional part. Now, do we make it a 3 or do we round it up to a 4? Maybe let me...
I would say 3 because of the maximum capacity of an integer, right? Is
Well,
that
no,
right?
I mean, integers can go, what do we say?
It can handle it.
Integer, yeah, integers can go as high as, it's so big I didn't even write the number out, I just said very large numbers. It goes into
Okay.
huge numbers, so.
So it doesn't really matter.
Right, it could definitely handle
Question.
a 3 or a 4, so, well, let me make it a little more extreme, 3.9, no. I'll make the float 3.9, which is really close to 4. Now, should it be a 4 or a 3? We have to get rid of the fractional part because we're converting it into an integer. But would we round it off to the nearest integer or just drop the fractional part? I guess, well...
I don't think it matters. Does it matter? Whether it's
It might
3 or
matter.
4, just as long as it's a whole number?
Yeah, but to the person writing the program, they might
Oh, okay.
care. But the compiler, let's just see what they decided to do. We'll compile it and then we'll run it. The results. What is it? It's a 3. So basically, the integer part is 3. The integer is 3. So it basically took the
It
3
rounded it down.
Yeah, rather it basically threw away the fractional part. So basically what we're saying is take the 3.9, convert it to an integer, which apparently drops the fractional part, doesn't round it off, and then take that result and put it into I. Now, if we took the I and put it back into F, would the 0.9 reappear or not? So I think.
Sorry, say it again.
So if we decided to go like this, like it's, suppose our next line was to take F and say that's equal to I. So in other words, I guess what I'm really just asking here is
If you've already declared I equals INTF, you mean?
Well, so basically what I'm really would be testing here is somehow does the integer have the 0.9 but it doesn't display it, but if you ever converted it back the 0.9 would come back, or would the floating point number now be just 3 or 3.0? And in this case, so I don't know, sometimes people think that.
Well, it's already been declared up top, so if you ever want it to come back, you just release it from the embedded code. Does that make sense?
Wait, so if I compile it, now see the floating point number is just, I just wanted to demonstrate that that 0.9 is gone. So the floating point number is now 3.0. So what I really did was, I had an integer which was equal to 2, a floating point number which was equal to 3.9. We took the 3.9, converted it to an integer, and stored that value into the I, then which is a 3, with the decimal gone. But sometimes people think the I still contains the 0.9 but won't display it. They think it's still hanging around. So if they put it back into the F, it'll show up again, but it doesn't. It's gone forever. It showed up as 3.0. Okay, so now do you think it would make sense to do, so now we're doing this typecasting, which is basically just taking types that we are using and converting them to other types and seeing if the compiler can figure it out. Should we be able to say to take a character and convert it into an integer? Does that even make any sense? So what I'm doing here is I'm saying I have a character which is equal to capital A. Take that character, convert it into an integer. Does that even mean anything? And if so, if you can perform the step where you can convert it into an integer, then store that into I and we'll print it out. What do you think would happen here?
Character into an integer.
So if we compile this, then compiled, the compiler thinks it knows what it's doing. I didn't save it. Sorry. That result did not look right. Okay, it compiled. Then I run it. And the integer value is 65.
So why did it do that? A, well what is A equal?
A, apparently A equals 65.
65? Where did
So-
that come from? Is that
So-
hidden somewhere?
Let's see, we can go out to the internet and bring up ASCII character map. Go to Google, check all the different characters. What do we say, 65? 65 is right here, capital A. So there's a map of
It just
character.
referred right to Google.
Well, no. I went out to go. So apparently it came out 65, and that means something. But so there's a standards ASCII, ASCII, a standard group of people that came up with definitions for what all the characters should have some assigned number to them.
What was the, I'm sorry, the code was I equals, what was in parentheses?
I equals the type you're converting it to, which is integer,
Oh, that's
and
right.
then C.
And C.
So basically we're taking a character, asking the compiler, can you figure out how to convert this into an integer? If you know how to figure that out, we'll accept it. And it apparently did, and it went to this chart. So the integer value for a capital A is 65.